Okay, so the last time we talked about the availability of polynomials. In particular, we looked at some criteria for irreducibility. So just repeat. So a polynomial f is called oh yeah, primitive. If the greatest common divisor of the coefficients is 1, so this is a polynomial with coefficients in Z. Then we have first the statement lemma by Gauss that if f and g are primitive polynomials, they have positive degree, then the product f times g is primitive. And then we were concerned with the irreducibility of polynomials. So an element in, say, an integral domain R is called primitive, is called irreducible. If we cannot write it in a trivial product of two factors, so that if this element is called A, so if whenever A is equal to B and C, with B and C elements in R, then it follows that B or C is a unit. There were some extra assumptions. Maybe we also need first that this should be a non-zero element and it should not be unit. Okay, and so then with this definition we find that this was this other lemma, so Gauss lemma, so if f in Zx is primitive, then it follows f is irreducible in Zx if and only f is irreducible in Qx. This is really not obvious because you have more possibilities of factoring things here, but still that's the way it is. And there are some criteria for the irreducibility of polynomials with coefficients in Z. And so this also gives us then the irreducibility in Qx. And the simplest one is the isocline criterion. So if f is a polynomial in Zx, which is primitive, but this anyway follows from what I said before, So if there is primitive and assume there exists a prime number such that, so I write f equals sum I equals 0 n x to the I, such that p divides a0, p divides a1 on, p divides an minus 1, but p does not divide an, and what? No, until now it's correct, and p squared does not divide by 0, so that's the statement. What? Does not, yeah. Then f is irreducible in ZX in QX. As I said in words, but didn't explain properly, this is somewhat more general. You could replace Z by something which is called unique factorization domain, which I haven't explained what it is. And a prime number you could replace by a prime element, which is an element in this domain which generates a prime idea. And then you would have here the same for Zx, and so Zx would be with coefficients in this ring, and this would be in this with coefficient in the so-called quotient field of fractions. So with the same proof would prove that. But as I haven't defined what this is, it doesn't matter. So, and the same also for the Gauss lemma in a similar way generalized. Now, we had seen, so just give one more little trick how you check. One can check that the polynomial, but there's maybe so one thing to check irreducibility is also to make some substitution. So one can substitute into the polynomial to check irreducibility. So if f is a polynomial, I from 0 to n, ai x to the I is a polynomial with coefficients in a field, and I take any element a in k, I can replace the variable x by x plus 8, so I can shift it by 8. So, right, f of x plus a, so sum I equals 0 to n. Maybe I shouldn't call this a, for this is maybe I call it ai x plus b to the I. So this I mean so you just multiply this out the way you would normally multiply out, collect the terms, you get a polynomial. Okay, so this is also an element of K. Then it is clear, then the original f is irreducible if and only if f of x plus a is irreducible. B, yeah, now it has become B. No, this is just because the map which I could call maybe sigma b from kx to kx, which sends polynomial f to f of x plus b. You can see that this is a ring homomorphism. In fact, a ring isomorphism. No, because in its sense, if you take the product of the sum of two polynomials and you replace x by x plus b, it's the sum, or it's a product, or it's a sum of these with x plus b. And if you take the product of two polynomials and then replace x plus b, you can also do it the other way around. So it's a ring homomorphism, which also says it's 1 to 1 and 0 to 0. And it's an isomorphism because obviously the inverse is sigma minus b. And so, thus, it says irreducible elements to irreducible elements. Now it has to send, it's an isomorphism, it sends units to units and products to products, and so it will send irreducible elements to irreducible elements. So, and reducible elements to reducible. And so we just look at one example which we'll use later. So let P be a prime, so a prime number in Z. So we look then the polynomial f equal to x to the p minus 1 plus to the p minus 2 plus and so on plus p plus 1 is irreducible. What?
Plus x.
What?
X.
Yeah, x. Obviously, thank you. Irreducible, in whatever qx. Well, so in this case, what do we do? If you write x minus 1 times f, this clearly is equal to x to the p minus 1, as you know, one of the standard, some kind of geometric series. And then, so if we now replace x by x plus 1, so we get, if we take x times the follows, x times sigma 1 of f is equal to, so if we apply sigma 1 to x minus 1, we get x, and then to f we do this, so this we get by replacing here x plus 1, so this is x plus 1 to the p minus 1, which is equal to whatever sum I equals 1 to p choose I. Yeah, I wanted to write it differently. So anyway, this is correct, but if I therefore sigma 1 of f is this thing divided by x, and so this is sum I equals 1 to p choose I, x to the I minus 1. And now it's standard that if you have such a binomial coefficient, p for a prime number, p choose I, when I is different from p, this is divisible by p, and when we also had something similar anyway, we proved the zero theorem, and obviously p choose p is equal to 1. So we have p divides p choose I for I from 1 to p minus 1. Obviously p choose p is equal to 1, and we also see that p choose 1, which is the coefficient of x to the 0, is equal to p, so p squared does not divide p choose 1. So it follows by the Eisenstein criterion that sigma 1 of n is irreducible. and thus representatives. Okay, so this is another such example. I mean, there are other tricks, maybe I will come back to that later. One other thing you could also do is kind of reduce everything modulo prime number. But anyway, this we maybe will see later. Let me see. Okay. Now I want to maybe finish with this and instead start talking about fields and field extension. So this is about. So we know what. So what we are interested in is field extensions. So and Galois theory. So if we have, we look at field extensions. So this, to begin, it's about fields, but we are interested in, want to study field extensions. So this means we have, say, K is a field, L is a field, and K is a subring of L. Then we say, that L over K is a field extension. And we want to understand something about field extension, particularly want to understand algebraic field extension. So an algebraic field extension is one where the elements, so if it's L over K, where the elements of L satisfy some polynomial equation with coefficients in K. Maybe it's A in L, polynomial equations. F of A is equal to 0, where F is a quantity coefficient in K. And we want to understand those. And so Galois theory allows us to understand this. The field extension in terms of a group. So the Galois group of L over K. Okay, so this is the program. We want to introduce this stuff and then use this Galois group to say something about field extensions. This has to do with the old problems of wanting to solve, to find solutions to polynomial equations. So one big problem which we also will talk about is whether you can find a solution to any polynomial equation, say over the rational numbers, in terms of just taking nth roots of elements and so on. So this is the solution by radicals. So by radicals, this was an open problem for a long time, and then it was solved negatively by the use of Galois theory. So that is actually not possible. So you can only do this for polynomials in general, only for polynomials of degree at most 4. And we will see. I haven't decided to explain the problem, I will come back to it when we are. Okay, so let me first now start with the definitions. So first I want to define the characteristic of a field. I also want to study fields of characteristics. So if K be a field, so the characteristic of K, so which is denoted characteristic of K, is the smallest positive integer with such that if I take n times 1, which means 1 plus 1 n times, that this is equal to 0 in K. Obviously this is not, such an integer will not always exist. For instance, the rational numbers n times 1 is never 0. So with the characteristic of K is defined to be 0 if no such n exists. Okay, so it means, for example, if we take the finite field Z modulo P times Z with addition and multiplication in the usual way, which is usually defined if you want to view it as a field as Fp for P a prime number. Then the characteristic of this thing of Fp is P, because obviously P times 1 is equal to 0 in this thing. On the other hand, the characteristic of the rational numbers is 0, because if we add up any number any number of times, we always get something non-zero, because we get just the number n. Okay. So, in fact, one of the first observations is that the characteristic of a field is either a prime number or 0. We mark the characteristic of K equal to 0, or the characteristic of K is a prime number for any field. Okay, for any field, it's either 0 or prime. So obviously, if the characteristic 0, the characteristic is 0. So assume it's not 0. So let n be equal to the characteristic of K. We have to see it's a prime number. So then n times 1 is equal to 0. So if n is not a prime number, we can write n times 1 equal to n1 times n2 times 1. And the way the distributive law works, this is the same as n1 times 1 times n2 times 1. And so in the field, obviously, we have no zero divisors. So if this product is equal to 0, then one of the factors must be equal to 0. And so as, on the other hand, this n was supposed to be the smallest such number, so that means that the only way this is possible is that if one of the numbers is 1 and the other one is n. If we have n1 is equal to 1, or n2 is equal to 1, and thus n is prime. Okay, so this is just the distributed law, and so we have this simple fact. So the characteristic is always primary. This does not mean that, as we will see, that every finite field has just p elements. There can be fields with more many elements. In fact, there are also fields of characteristic p with infinitely many elements. Although we will not talk about them, but in certain okay. Now I want to talk about these field extensions. So the subring K of L of the field L is called a subfield well, if K itself is a field. Obviously, reduced structure, and in that case, we call L over K a field extension. So, whatever, for instance, the example is that Q is contained in the real numbers, is contained in complex numbers. These are all field extensions. So we will later, this Gottshe group has something to do with this homomorphisms of fields. So I want to introduce already the notation. So if L over K is a field extension, and large K over small k are field extensions, so a homomorphism of rings and therefore fields from L, so I say phi, from L to K, is called a K homomorphism. If I take phi and restrict it to K, which is contained in this is just the identity of K. So we have K is contained in L, K is contained in large K, and so we have a homomorphism from one to the other, which is the identity on K. This we call a K homomorphism. So for every element of K is sent to itself, and something else happens to the other element. And if it is also an isomorphism, automorphism. And you can imagine if it's an automorphism, which means the homomorphism to itself, say from if L is equal to K, it's called the K automorphism. And so this has a, we see that these automorphisms play a big role in understanding this. So now, however, this we will not use immediately, but I just wanted to. I also want to briefly say, maybe just as another remark, to finish this thing with the characteristic. So, if L over K is a field extension, then it follows that the characteristic of L is equal to the characteristic of K. And this is actually quite obvious because you know that so K, the subfield K will always contain the element 1. So it also contains all the elements n times 1. And so if that is 0 in K, that's the same condition as if it is 0 in L. So 1 is an element in K, plus n times 1 is an element in N. So somehow one doesn't see, one only sees them, for the characteristic one only sees the multiples of n, and these are all in K. Okay. Here. Yeah, so now we want to come to our first little theorem, which is the degree theorem. So this is a very simple fact. If you have a field extension, L over K, it follows quite directly from the definitions that L is a K vector space. And we then define the degree of the field extension to be the dimension of this K vector space. And then the degree theorem says that if you make two field extensions in a row, then the degree multiplies. Okay, so let's go to this. So first, what I said about this vector space, we mark. So let L over K be a field extension. Then, obviously, we certainly have that L with the addition is an abelian group. No, because that's part of being a field. We can restrict the multiplication in L to just K times F, so that we only allow ourselves to multiply with elements in K. So, and restriction of multiplication from L times L to K times L gives a scalar product. So from K times L to L, which just sends an element A here in K, and therefore X, the element in L, sent to A X. It's just a multiplication in L, but we only allow elements in K here. And we have some obvious laws. We have the distributive laws for this. So there's distributive laws. Namely, so if we take A plus B times x, this is AX plus BX, where we are obviously A and B are elements in K, and X is in L, and A times X plus Y is equal to AX plus AY. So we have this distributive laws. This is just a restriction. We have the distributive laws in the, for the multiplication in L times L, so we certainly have it in this situation. And we have the associative law. So if I take AB times X, this is A times B times X. Over again, B and B and K, X and L. This is because this holds for any such things where all three of them are out of L. And also we clearly have that 1 times X is equal to X for all X and L. This is also clear. And if you go back to linear algebra class, these are the actions of a vector space. So these are, so it means L is a K vector space. So the definition, just so we're just restricting the product like this to multiplying only with elements in K, we get that L is a K vector space. And so we can then define, as I said, the degree of L over K, so L over K of the field extension L over K is just the dimension of L as a K vector space. So here, for simplicity, so I just say the dimension is infinite if it's infinite dimensional, otherwise it's a number. Oh, so this thing. If L is infinite dimensional. I'm not interested in further subtleties about how infinite it is. Okay, so this is the degree. And now we could ask ourselves what happens to the degree if we iterate field extension. I will also introduce another word here that we often use, definition. If which we want, yeah, so L over K, small k, and large K over L are field extensions, we call L an intermediate field of large K over small k. Okay, so this would be the field. And then the statement is the degree theorem, which is very elementary, but it's kind of something that we'll use all the time. Degree theorem. So assume we have such a field extension, so at L over K, and K over large K over L field extensions. Then we have that the degree is multiplicative, so then the degree of large K over small k is equal to the degree of large K over L multiplied by the degree of Lk. So with the convention that if any of these are infinite, then the other ones are infinite too. So, I mean, with the convention that infinity is equal to infinity times n is equal to infinity times infinity. So, I mean, whenever one of these numbers is infinite, then this is also infinite. And obviously, okay, so this is just the convention. And then the statement holds. So that means this field extension k over k is, the degree is finite if and only if both of these are finite. In that case, the degree is the product. If any of these is infinite, then this will be infinite too. So let's prove it. So it's clear if L over small k or k over L is not of finite degree. Maybe I should, well, I can introduce this later. Is of infinite degree. Then also k over k is infinite. No, just because you have a, I mean, it's almost directly from the definition, because for instance, if this degree is infinite, that means there's no finite basis of large K over L, but K is even smaller, so there can be no finite basis here, and in similar way the other round. So let's, maybe I should have introduced this here. Maybe I just write it because I want, it's a convenient language. So if L over K is finite, so if this degree is finite, we say the field extension L over K is finite. Okay, it's just some simplified language. Okay, now let's go to the proof. It's actually quite easy. I mean, you can somehow see, you take, I mean, if you take a basis of large K as an L vector space, and the basis of L as a small k vector space, then the basis of large K over small k will be given by all the products of the basis elements here multiplied with the basis elements here. Let's see how that goes. So assume, so let K over L and L K finite, and let the x1 to xn be a basis of, say, which one did I want? First L over K, and y1 to ym be a basis of large K over L. So the claim is, if I take the set of all products xi times yj, where I goes from 1 to n and j goes from 1 to m, these are all different, and these are a basis of large k over small k. Okay. So if you want to check this claim, you just have to check the obvious thing. We have to check that these span large k as a small k vector space and that they're linearly independent. We just check this. So they generate so that means let's take any element y in k. Now we know that this element, so that these form a basis of k over L, so therefore we can write this y as a linear combination of these yj's with coefficients in L. So then there exist, how do you want to call them, b1 to bm in L, such that y is equal to sum I equals 1 to m bi y. Okay. Now these y are some elements, these bi elements in L. So each of them can be known as this is a basis of L over k. Each of them can be expressed in terms of these basis elements here in the same way. So which one is it? For each j, this I want to call j because it's better. So for each j from 1 to m, we can write bj as again the sum I equals 1 to n aij xi, where the aij are elements in k. No, this is because these form a basis of k. And then obviously we just put it together. Thus, our element y is equal to the sum over I from 1 to n, sum j from 1 to m aij xi yj. Okay, so that's just, and that means that these generate. Now we have to see their linear independence. This is not more difficult, so they are linearly independent. So we assume we find a linear combination of them which is 0. We assume we have sum I from 1 to n, sum j equals 1 to m aij xi yj is equal to 0, and the aij elements in k. We have to show that all aij's are 0. That's what it means to be linear independent. So, first, these yj's, so I can bracket it like this. These yj's are linear independent, and these are elements in L. So as a
The index are
what?
the index, the order of the index are now. Okay.
No, it's the same index that I had before, I think.
Yeah, but outside J inside.
Oh, okay, yeah. So in that sense, it's wrong. You're right. So this is j equals 1 to m yeah, if I want to bracket it, obviously I have to do. Okay, so now I am allowed to put these brackets. Okay, so as I said, this is an element in L. So as y, j are independent over L, it follows that sum I equals 1 to m n this was no and aij xi, so this yeah, but this is equal to 0 for all j. And then the same argument again shows that all of them are 0. So as the xi are linearly independent over k, it follows aij is equal to 0 for all j. Okay, so that's quite simple. So in particular, we see a few things. There's some restriction on what kind of intermediate fields they can be. For instance, we have the corollary. So if L over K is a field extension, so say a finite field extension, so maybe K over K is a finite field extension, and L is an intermediate field, then follows obviously, shown later on, that the degree of L over K must divide the degree of large K over K. So in particular, for instance, if the degree of this field extension is a prime number, there can be no non-trivial intermediate field. So if K over K is a prime number, I should say have set this too. The only intermediate fields of K over K are large K and small K. I should maybe make it clear. So just so that it's written, so the mark, I mean, this is clear. No, the degree of any intermediate field must, so if this is, so we see from this that this divides it, and if this number is a prime number, then either the first degree or the second degree must be equal to that number, and so we get this. So, and the only thing that maybe, just to be sure, so if you have a field extension, if the degree of L over K is 1, then L is equal to K. So we use that here too. Now this is just because clearly in this case 1 is the basis of L. L is K vector space. So thus we can write every element of L, so the size plus, I never have this now, maybe you can write it here. So L is therefore equal to K times 1 equal to K. No? you know, that the vector space is one-dimensional means that every non-zero element is a basis. And so I can do this. Okay. So this was the theorem. Okay. Now how much? I want to talk about algebraic extensions. So an extension would be called algebraic if every element from the bigger field solves a polynomial equation with coefficients in the smaller field. Which one? Okay. And then we will be mostly interested in finite algebraic extensions. So definition. Let L of K be the field extension so first we say an element from the bigger field is called algebraic over K. If it satisfies polynomial equation, so if this polynomial f in kx, so with coefficients in the smaller field, which is not the zero polynomial, with f of a is equal to 0. Okay, so if it's a zero polynomial with coefficients in the smaller field. So L is called algebraic over K if every element in L is algebraic over K. By the way, I forgot to mention, so an element which is not algebraic is called transcendent. Kind of a fancy name. But anyway, so A is not algebraic over K. It is called transcendent over K. So just as an example, so for instance we take square root of 2 is algebraic over Q. Because obviously the polynomial would be x squared minus 2. So if I take the complex unit I is algebraic over Q. In this case, we can take the polynomial x squared plus 1. So it's a 0 set polynomial. And examples of numbers which are not algebraic are, for instance, e and pi are transcendent. These are remarkably difficult to prove, but it was shown, like, I think in the late 19th century and at the turn of the 20th century, it was shown that these two elements are transcendent. And you can, more generally, one can easily show that most real numbers are transcendent in some precise sense. So they're
algebraic are countable, right?
Yeah, algebraic numbers are countable, and the other real numbers are uncountable. So there are many more transcendent numbers than, but that doesn't make it easier to prove that a given number is transcendent. But there's also some other thing. You have some criteria. If you have something like, if you have a number which you can approximate very well by rational numbers, and it's not rational, then it must be transcendent. So if you take something like some something like that, there is a theorem which says that something where, so you can approximate it in steps by rational numbers incredibly fast, and this makes sure that it is not algebraic. So this is also transcendent. There's some criteria like that, but this we will is also transcendent. So this is anyway. We will not be concerned with this, but I just want to mention. Okay, so now we want to look at the extent. Already there? Yeah. Now I want to look at the extension generated by some elements. We've seen look at extension generated by some algebraic elements. So definition. If I'm given some elements, in some field large K, and so maybe I say let large K over small k be field extension, and I take some elements A1 to An from the bigger field. So the extension of K, of small k, generated by A1 to An will be, well, it's supposed to be the smallest subfield of K which contains, of large K which contains small k and which contains this element. So it is the intersection of all subfields of K, we should have put it there, K, which contain small k and A1 to An. So obviously, if you have an intersection of fields inside a given field, this will also be a field. So this is a field, and by definition it contains K and it contains A1 to An, and obviously by definition it's the smallest subfield of K which contains all these elements. So this is, we have already several things how something is generated by something here. For field extensions it makes it bigger because in fields you have more operations than other things. So it's the smallest field which contains these elements. And so we will want to study this in particular when these elements are algebraic. So the main case that we want to study is actually the case when we just have one element. So, did I write it? And so it is denoted K A1 to An. K with round bracket. So this is you know, anyway, maybe I don't take more comments. So now we want to, so particular nice case is the extension generated by just one algebraic element. So this is, so I even give it a name. So let A in L be algebraic over K. So again, L over K is a field extension. And A in L algebraic over K. Then, so this extension given by this one element is called a simple algebraic extension. So these will be particularly important to us for two reasons. First, we'll see in a moment that they are very easy to understand. And second, we will show that under some reasonable assumptions, all finite algebraic extensions are of this form. So they are easy to understand, and every field extension you want to consider is like that, so that seems very good. But obviously, there are some subtleties. But anyway, so we, in some sense, everything can be understood in terms of simple algebraic extension. Okay. So let's. So we want to understand such a. Such a field extension can be completely understood in terms of the so-called minimal polynomial of A over K. So this is somehow, in a simple sense, the smallest degree polynomial in Kx, such that A is a zero of it. We also make it monic to make it unique. And somehow, in terms of this polynomial, you can describe this field extension completely. So, let me explain this. So, first, I think I already had this, but I repeat it. A polynomial f in Kx, the K is a field, is called monic if the leading coefficient is 1. So now I didn't write it, I just write in words, if the leading coefficient. So it's clear that, by multiplying just by an element in K, I can always make a polynomial monic, and by a non-zero element in K, so by multiplying by unit. So by definition, so for every, if I have an element f in Kx, which is not zero, and there is a unique monic polynomial G, well, it's obviously not zero, which generates the same idea in Kx. Just if I, here I just divide by the coefficient of the leading, by the leading coefficient, this gives me another polynomial, and obviously they generate the same idea, and it's the only monic ones which does that, because to generate the same idea, they have to differ by multiplying by a unit, and the units are just the non-zero constants, and so this is clear. Okay, and so I give two definitions for this so-called minimal polynomial that we use here, which are sometimes one uses one, sometimes the other. So assume we have this A in L algebraic over K. Again, lower K is a field extension. We can look at the evaluation morphism at A from Kx to L, which sends a polynomial f to f of A. We know this is a ring homomorphism. And so this the fact that A is algebraic means there are some polynomials which are zero at A. So some non-zero polynomials which are zero at A, so that means the kernel of this map is non-zero. So A algebraic means the kernel of the evaluation at A is non-zero. So it follows that exists. So we know, so as Kx is a principal ideal domain, every idea is a principal idea, so we have that there exists a unique, so it means that this kernel is a principal ideal, and so therefore there exists a unique monic polynomial which generates this kernel. We'll call it like this, with the kernel of the relation at A is equal to the idea generated by Fa. So this Fa is called the minimal polynomial. Of A over K. So this is one definition. But you can also describe it, so it's just, so it's a bit indirect and abstract. So you say, okay, you evaluate this, the things, the polynomials which vanish, they are formed an ideal which is generated by a unique monic polynomial, and this is called the minimal polynomial. But you can also describe it much simpler, so have a criterion for the minimal polynomial. So this is the following proposition. So again, A in L, the algebra over K. So the minimal polynomial of A over K is unique, irreducible, monic polynomial say f in Kx which vanishes at A. So in particular, no, just as a title mark, so if A is an element in K, then the minimal polynomial, so f of A is equal to x minus A. It's irreducible, and So now let's look at this. So try to prove this thing. It follows quite directly from our definitions. So we first want to show that the minimal polynomial as defined here is irreducible, because that's not written here. So show to assume we can write it as a product of two polynomials. So where G and H, so irreducible obviously in Kx. So where G and H are polynomials, coefficients in X. We have to show that G is a constant or H is a constant. So we know that fa of A is equal to 0. And we can write it out. This is G of A times H of A. So it follows, as this is without zero divisors, it follows that one of them must be 0. So obviously we can decide, it's our business whom we call G and H among those, so we can assume that G of A is 0. So if, say, G of A is equal to 0, then G is indeed in the kernel of this evaluation homomorphism at A, which is the idea generated by FA. So it means G is a multiple of FA. So I can write G equal to L times FA. So, but if I write this like this, so thus it follows that FA is equal to G times H is equal to L times H times FA. So, and this means, because we are in an integral domain, that L times H is equal to 1. And thus H is a unit. It's an element in case study. Okay, so we saw that FA is irreducible. Okay. Now we wanted to show, on the other hand, in order to show that this is precise, that we have precise the statement is, we have to show that if we have a monic irreducible polynomial with this property, then it must be this minimal polynomial. So conversely, let G be a monic irreducible polynomial in Kx with g of a equal to 0. Well, again, we can see then it follows G is again in the kernel of the evaluation homomorphism, so G is in the ideal generated by Fa. So thus G is equal to H times Fa with H in Kx. So as G was irreducible, it follows that H is an element in K star. And as both G and Fa are units, it means the leading coefficient here is multiplied by this H, so the leading coefficient must be 1. So they're both monic, so the leading coefficient must be so. As G and Fa are both monic, it follows H is equal to 1. And so they are equal. Okay, so this is this other way of describing the irreducible this polynomial. So I don't have much time. So let's just as an example. So for instance, P is a prime number. So actually I don't need a prime number, but it doesn't matter. So let P be a prime number. You can maybe think how you can generalize it. So by the Eisenstein criterion, we have that x to the n minus p is irreducible for any positive n. So it follows that x to the n minus p is the minimum polynomial of, say, the nth root of p over q. So it's irreducible in Qx. Okay, so this is just an example. Now let me see, I have only 5 minutes, so at least I can state the next theorem. So now I want to use this minimal polynomial to describe the field extension explicitly. And it's a quite simple fact, so this is the theorem. So let A and L be algebraic over K. It's always understood that K over this field extension with minimal polynomial. Fa. Then we have the following statements. First, this simple field extension Ka over K. So the Ka is isomorphic as a field to the polynomial ring Kx divided by the ideal generated by Fa. Okay, so this is in some sense a complete description. So it's isomorphic to this ring divided by this ideal. And from what we said, it follows that it's the maximal ideal. But anyway. And secondly, to make it a bit more concrete, the degree of the field extension is equal to the degree of F. So maybe write this in front of degree M. So M is the degree of the new polynomial, so this has degree M. And in fact, I can say what the basis is, and I take elements 1, a squared until a to the m minus 1. This is the basis of Ka as K vector space. Okay. You see whether there's one case where we can do the first statement. So we use this evaluation homomorphism. So maybe we'll only prove one next time, which is a long time in the future. We look at the evaluation homomorphism from Kx to now Ka, which sends the polynomial g to g of a. Okay, let's look at this. So this is a ring homomorphism, as you know, with kernel. The idea generated by Fa. So therefore, by the homomorphism theorem, the image of this morphism is isomorphic to this quotient. So let, how do I want to call it? L prime will be the image of this evaluation morphism. So by the homomorphism theorem, A prime is isomorphic to Kx divided by the ideal. No, this is just if you have a surjective ring homomorphism, the target is isomorphic to the source divided by the current. So now we have to see that, however, this we have to show the map is surjective. So as Fa is irreducible, we have that Kx is a principal ideal domain. Then we know, and Kx is a principal, and Kx is a principal ideal domain. We have that, and in a principal ideal domain, if you take the idea generated by an irreducible element, it's a maximal ideal. We get that Fa is a maximal ideal. Thus, we have L prime is a field. We have, and furthermore, we have, and so L prime is a subfield of K there. And as, obviously L prime contains K as the image of the constant polynomials because it's the identity on constant polynomials. no, a constant polynomial. If you have a constant, you put a into it, it doesn't change anything. No, as a evaluation of k. And if I take L prime, if I take the evaluation of a at a of x, this is equal to a. So thus L prime contains k and a. So it's a subfield of Ka which contains both k and a. But Ka was the smallest subfield of L which contains them. So it means that they're equal. Thus L prime is equal to k by definition of Ka. So therefore this map is surjective. Yeah, maybe, well, I don't know, maybe I will just torture to finish it. It's almost done. Then next time we review it, but it's quite simple. So we have shown, so now the second part, we have shown that that the evaluation at A from Kx to T of A is surjective. No, this we shown here. So thus it follows that you can write Ka as the image of this. So this is the set of all G of A with G is Kx. That is the definition of the image. So now we want to show that the statement was that 1 until a minus 1 are bases. So we take 1, so first 1, a equal a m minus 1, m was the degree of a, generate Ka is K vector space. So let's take any element in K. By the above, we can write B equal G of A for some polynomial. So if the degree of G is bigger or equal to the degree of Fa, we can use division with rest. And get that G is equal to Q times Fa plus the rest, where the degree of R, where either R is equal to 0 or the degree of R is smaller than the degree of Fa. Okay, so let's write the rest. So if the degree is 0, okay, then G of A is equal to 0. So that's not the So anyway, we have this R. So we can write so S Fa of A is equal to 0. It follows that R of A is also equal to 0. No, because there's G of A is that G of A is equal to R of A. That's what I wanted. Oops. Sorry, confused. So therefore, if we write G equal to sum I equals 1, 2. So whatever. I can write it, so this is smaller than m, so I write here m minus 1 so where the other ones could be 0. So pi x to the I. Then, by what I said, we have that sum I equals 0, m minus 1 pi a to the I is equal to our element of a is equal to b. And this means precisely that these elements 1 equal to a to 0 until a to the m minus 1, no, it's a linear combination of these, so these elements generate. And it's also easy to see they're linearly independent. So it's basically this turned the other way around. So assume we have a linear combination of them which is 0. So sum I equals 0 to m minus 1 pi a to the I is equal to 0. So then we can put g to be the polynomial corresponding to this. X to the I. So this is the polynomial which evaluated at a has 0. So it means this is G is an element in the kernel of the derivation at A, which is generated by Fa. So it's a multiple of Fa. But Fa has degree m, and this has degree m minus 1. This is only possible if G is equal to 0. And this means all these coefficients pi are equal to 0. This means the ai are linearly independent. Okay, so this was this result. Okay, so we will see next time what one can do with this. Anyway, I will not see you for the whole next week, I think. So I'm here on Monday, but otherwise I come only back the weekend after next. So have a nice week and don't forget everything.